Today we're going to go on with this new topic, which you can think of as being the whole rest of the course, just about, which is what I would call constrained motion. And I'll try to explain to you what I mean by constrained motion and how it's different from what we've been doing so far. But first I want to do an example of constrained motion. It's like the homework you have due tonight. It's like last lecture, and it goes like this. I've got these two pulley systems, and they're the same pulley system. And I think for variety, I want you to do this individually, without discussion. So I want you to think about it by yourself. So we're going to take these pulleys, and we're going to assume that that we can neglect the inertia of the pulleys, and that means both the rotary and the translational inertia. And we're going to assume that we can neglect the friction in the bearings of the pulleys. And we're going to assume that we have inextensible strings. Inextensible strings. Now, often when we make these kinds of assumptions, they are reasonable assumptions. If we took and made the problem and built it, they get about the right answer. In this case, it turns out these are somewhat unreasonable assumptions, that we'd have trouble duplicating the result I'm asking you to calculate. So it's somewhat of a mathematical problem in that if I tried to build this, I would not get the result, in that it would be very hard to make these assumptions valid. And what I'd like to do is compare two cases. One case is where I put a force here and a mass here. And another case is where I put a mass here and a force here. And it will be the same force. And what I would like to compare is, let me call this point A, and I can call this point B, and I can call this point C, and I can call this point D. And the question is, what's the ratio of the acceleration of A to the acceleration of D? And they're in different directions, so I'll put an absolute value sign over this. And I'll give you some choices: A, B, C, D, or E. And to make it so that you don't have to guess, I'm going to put numbers there. I could just leave it like that, but then it would be a course in ESP, not a course in dynamics. OK, so what are the possible numbers I could put here? Let's see. Let's put 1,000, about 1,000, about 1 over 1,000, about 1,000,000, about 1 over 1,000,000, and none of above. So I'd like you to work on this by yourself, or would you rather work in teams? Quick vote. Rather work in teams or rather work by yourself? Teams, raise your hand. Work by yourself, raise your hand. OK, you win. Work in teams. Ask me a question about the question. If you have one, TV can go off for a minute or so. When half of you have voted, I'm going to call time and make the rest of you vote. OK, 10 seconds left to vote. Now, would you like to play the social dynamics game and see how the others voted before I close it up? Yeah. You think that helps you or hurts you? Okay, can you see that? Is that clear enough, or do I need the screen? Clear enough. Okay, now the vote's still open. Coming down to a two-party system here. Okay, we're going to lock up the vote. Ready? Vote's locked up. Oh. Vote's locked up. Okay, so you're all doing, except for a few of you, something right, which is figuring out which one of these is bigger. So what you see is that, say in this one, we're pulling on this, and it's very sluggish because you got to pull on this, and this thing has to move a lot, and a lot of stuff this force is doing a lot of stuff, so the force doesn't accelerate much. So that means that these are good answers, and maybe that's a good answer. Now, last class, remember, we started with one pulley, and somehow we dug out the number 16. And it seemed implausible to most of you at the first. Now we've got 5 pulleys. How big a number could we pull out of 5 pulleys? Anybody want to make a case? You want me to just tell you the answer? Okay. This tension is half of that force. This tension is half of that force. This tension is half. This tension is half. This tension is half. 2, 4, 8, 16, 32. This tension is 1/32 of that force. So this force has an acceleration of F over 32m. But if you look at this mass moving, this pulley only moves half as much. This one only moves half as much as that. This only moves half as much as that, right up the line. So this only moves 1/32 as much as this. So it only has 1/32 the acceleration. But this only had 1/32 the acceleration of F over m. That's a factor of 1,000. So this only has an acceleration of 1 over 1,000 times F over m. So the acceleration of A is equal to F over 2 to the 10th m. Any questions about that? Yes?
Wasn't the ratio like 16 for when it was one pulley?
Just one pulley, right.
Why wouldn't it be?
Well, it's a different mechanics problem. And what is 16 to the 5th? Yeah, there you go. It actually works out right. But I don't like that reasoning. I'd rather look at this problem. It's a different mechanics problem. Right? There's 5 pulleys, but anyway, it comes out 16 to the 5th. But I wouldn't trust that reasoning. Okay, any other questions? Yes?
Where did you get 2 to the 10th from?
Half the tension, half the tension, half the tension, half the tension, half the tension. That's 2 to the 5th. Half the acceleration, half the acceleration, half the acceleration, half the acceleration, half the acceleration. That's another 2 to the 5th. So it's 2 to the 10th. Okay, now we do this one. Here we have a force, but twice that force gets here. 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 Twice that gets here. I did that 5 times. This force is 2 to the 5th times bigger than this one. But when this accelerates, this has twice the acceleration. This has twice the acceleration, twice the acceleration, twice the acceleration. So the acceleration of d, or at least the magnitude of it, without worrying about the plus and the minus, is 2 to the 10th times F over m. And so the right answer here is 2 to the 20th, which is about equal to 1,000,000. So there's your right answer. Okay. Now, pulleys, this vague thing that amplifies, attenuates, and so on, it lets you know that you've got to pay attention to what the pulley is doing. Simple problem with 5 pulleys. We just start with the picture before we put up anything here, where we put the masses and F's and what we're paying attention to. But there's a simple 5 pulleys, and if you set it up wrong, think about it wrong, you're not just off by a little bit, you're off by a factor of 1,000,000. So if you want to say, I get it, you've got to make sure you can get those factors of 1,000,000 right. Okay, any questions about this? Video off. Off. I think I have to tell my computer which is the right answer. Okay, and then we close up shop here. Okay, now we want to go on to constrained motion. And this is stuff where we do not know the forces given the positions, velocities, and time. Forces not determined by position, velocity, and time. So what would be examples? Examples are string, and this is inextensible string, rods, hinges, contact, welds. And these are different from the things we've been doing in the past. In the past, these CS people don't know how to erase a blackboard. You have to teach them better. This is different from cases where material properties tell us the forces. And that would be, for example, springs, dashpots, gravity, air friction. So these are the problems where if you're given the position and configuration, you can find the forces. And until last class, those were all the examples we were doing. So I'm now going to show you a trivial example. It's so trivial that it's hard to see the example in the example. But if you think about it, maybe it will help you later on. So the example is we want to contrast this situation where we put a rod between two masses and we apply a force like this, and we want to compare that to the situation where we put a spring between two things and we apply a force. So here's a spring, and here's a mass and a mass. Now if we draw free body diagrams of this, we cut this string, we have a tension. We draw a free body diagram of this, we cut this string, we have a tension. And we go over here and we've got this force. And when we draw free body diagrams in this situation, we cut this spring and we've got a tension. We cut this spring here and we've got a tension, and we've got this force over here. So here's the free body diagrams in this case, and here's the free body diagrams in this case, and the free body diagrams look exactly the same. But they're not the same mechanics problem. So when you draw free body diagrams, you cut things and you show the forces, and these two things look the same as far as the free body diagrams go. The question is, how do we figure out the forces at those cuts? So in this case, we have that the tension is equal to K delta L. And in this case, we have the tension equals, how do we figure out what that tension is? Well, to start with, you think, oh, it's a string that's not extensible. That's simpler than a spring that's got stretch, and I've got to worry about deformation. But in terms of dynamics, the simpler problem becomes the harder problem. The constraints make it harder rather than easier, which is almost backwards from statics, where constraints made things easier rather than harder. So if I just to make it a little graphic, so you can just have something, a cartoon in your head, I need 2 volunteers. I need to rope in 2 volunteers. 2 volunteers. There's 1. Another one. Another volunteer, please. Come on. There's 100 people out there. Come on. What? Okay. This is a simple demo. This is really simple. Okay, put your hands in the air. Okay. Come back over here. Hands in the air. Okay, so these guys are tied together. Now, come back over this way. Now, the distance between them is fixed. Keep that taut. Now walk back and forth, keeping that taut. and there's a constraint that these two have to move together. Okay, come back over here. Okay, now I'm going to pull on them and make them come over here. How much is the acceleration when I pull on them? There's this constraint between them. And if I want to figure out this force, how would I figure it out? Well, if I model this as a spring, which you could, and I knew how much it would stretch, just stretch 1 inch or a centimeter. It's a low note. You can't hear that. It's like 10 hertz. You can't hear it, even with a good mic. If I model this as a spring, and I know the stretch, like in 202, I could calculate this. But if I think of this as inextensible, I can't figure out this acceleration, assuming the string is taut, without knowing, for example, how much one or the other accelerates. So it becomes a harder problem. Now, there's a way of getting around this, which is if I pull on him, I can think of the two of them as a system with a mass of 2m. Then I can calculate the acceleration, because it's a force divided by 2m. And then I know he's accelerating with that f over 2m, so I can calculate the tension is the acceleration times the mass, f over 2m times the mass, m. There's a force over tension is half of what I'm pulling, which you get intuitively. But you have to go through the mechanics calculation to get the answer, which is different from the case with the spring. So you have to use the kinematics to get the answer. On the other hand, there are tricks to get around it. So there's two things. Either you use the mechanics to get the answer, which makes it harder, or you have to use tricks to get around it. You somehow have to finesse the problem by finding some tricky thing like momentum balance. So we find the tension by either solving for accelerations, or B, we avoid finding the tension and we so-called finesse the problem, which means we find some tricky way to do the mechanics without ever finding a constraint force. And that's basically all of advanced mechanics, is doing tricky things to avoid finding constraint forces. And as you saw in the pulley problems, it can be somewhat of an exercise. What you notice in the pulley problems is to solve them, you have to put the geometry explicitly into the problem in the equations of motion, which is different from the satellite problems and the drag problems and so on, where you just get the equations of motion directly, then you solve them. Okay, any questions about that? Okay, now moving on from pulleys, we want to do harder problems like 2D, 3D problems. And I'm now just going to start right in with an example. If you get this example, you will have then learned something in the class. So to start with, it seems like a simple example. You'll find it surprising that you don't know how to do problems like this already. Then you learn how to do them, and then you're a better person for it. So here we're going to do a car. And there's a whole set of these two-dimensional car problems. Let's do it in 2D. We can do it in 3D. Same idea, just you have to be even better with vectors. We can do a car braking or a car accelerating. We can do rear-wheel drive, front-wheel drive, rear-wheel brakes, front-wheel brakes, four-wheel drive, all different problems. I'm just going to pick one at random. So I'm going to do accelerating. So it's one of a set of, I don't know, 6 or 8 car problems. Accelerating with rear-wheel drive. And then we're going to make a bunch of standard assumptions about how cars work in simple models. So here we have this car. And it's got some obnoxious driver in it. And so it's accelerating like crazy with the rear wheel skidding. So the rear wheel is skidding because it's got a huge, powerful engine. It's like 3 a.m. Saturday. You're trying to go to sleep. Somebody's screeching and showing off, like screeching back here. On the other hand, this wheel has good bearings, which means we're going to neglect the torque at the hub, and it's got negligible inertia. Negligible inertia. So in effect, this becomes a good ideal wheel, which means there's no tangential force. You have all that good rubber with high friction. You're not using it to speed up or slow down the car. Back here, we've got this rubber with friction, so there's a coefficient of friction here. Let's assume we know it is mu. Now, we'll have to assume some things about the geometry of the car. For example, we have to know where the center of mass is. Let's assume we know it's the height h above the ground. We have to figure out where that is relative to the parts of the car. It's tempting to label distances like this A and B, but that's a bad idea because we use the letter B for A for acceleration, rather. So I'm not going to do that. I'll label them B and C. So tempting that even when I'm trying to tell you not to do it, I did it. In case I want to get this length here, I put this length like this. So I've got this geometry. I'm going to assume the car is going forwards like this. So there's the velocity and acceleration. Now, I can assume more things. So this will be like a kinematic constraint. And it's not a real constraint. It's just one that we use to make the problem understandable, is that the car has a stiff suspension. So we say the car doesn't rotate, and the wheels stay on the ground. Now, it's possible that the car could do what's called a wheelie and pop up in the air, and it's possible that the suspension has some springs in it, so it tips around a little bit. But we're going to make the idealization that the suspension is stiff and it doesn't tip around, and we're going to assume that it doesn't pop up in the air, but we can check that afterwards. How do we check that is we'll look at the reaction force here, and when we calculate this so-called constraint force, we'll make sure that it's not in tension, the ground doesn't suck. If in our calculation the ground does suck, we say we made a mistake by assuming it didn't do a wheelie, therefore it probably did do a wheelie. So without actually doing the calculation of the rotation, we can check and see if it rotates or not by assuming it doesn't, calculate the reaction force, look for a contradiction. If we don't find a contradiction, it didn't rotate. If we did find a contradiction, it did rotate. We did the problem wrong. Now we want to do the problem right. Well, you've got to wait a few weeks to learn how to do that. Okay, so this is how we're going to deal with this problem. How are we going to solve this problem is we're going to draw a free body diagram. So we can draw a very idealized free body diagram of this because it's maybe a relatively hard problem, and you don't want to distract yourself with such a fancy picture. So the key thing in the free body diagram is we have a point of contact here. So we can call this A, capital A. We have a capital B. We have a G. So we have these three main points, and we can just make our conceptual car like this and put here G, and here's A. And we've cut the ground away here, we've cut the ground away here, and here's A, G, and B. Any questions about this picture of the car and how it relates to that picture over there? It's a very schematic picture, but that's all we need for the free body diagram. Now we need to put the forces on the free body diagram. If we're going to use some coordinate system, we have to put that on the side. So I'll put unit vectors here, I and j, to show what I mean by x and y directions. Sometimes we might make those crooked one way or another. And we've got to start filling in forces. So the first thing is we have to fool this thing into thinking the world is underneath it. And we fool it by applying a gravity force. So I can put mg like this. Or I could put an alternative I could have used there is I could go like this and go minus mgj. Either of these would be fine on this free body diagram. Now I've got the front wheel. On the side somewhere, maybe I've drawn a free body diagram of the front wheel, or maybe I've done so many of them that I don't have to draw this diagram again and again. And I find that there's no friction at this bearing, so there's some reaction force here. I don't know what that reaction force is. Then I take sum of moments about this point is equal to something about the dynamics plus the torque over here. But the dynamics, I assume, is negligible. I've neglected the inertia, so this goes away when I draw the ideal wheel. So you can read about ideal wheels in the book, but the assumption is if there's no bearing friction, no torque here, negligible inertia, that thing has to be 0. So the wheel has the job of making it so there is no reaction force along the motion. That's what wheels are for. So there's no tangential force here. On the other hand, the back wheel has a big torque. The motor's applying a torque to it. The rubber's screeching. They're sliding. Therefore, they're sliding with friction. Therefore, there's a force resisting the sliding. The wheel is spinning like this. It's sliding that way. The force resisting the sliding is that direction. So there's a force in this direction like so. And I'll draw a nice big force like that. And I can either say the ratio of the sideways force to the vertical force is mu to 1, or I can say this acts at a friction angle phi, where I've given that mu, which means I'm given implicitly, I'm given phi with tan phi equals mu. It's just an equivalent way of giving the coefficient of friction to give the friction angle. And now I've got a free body diagram of this thing, and I want to figure out what's going on with this. So any questions about what I have so far? And what do I mean by questions? Imagine a big water bomb explodes, the blackboard's erased, I disappear, and you've got to reproduce it yourself, or the world's going to blow up. Could you do it? Yes? Here are we looking at or over there? Yes?
Is that just the normal force that's pointing upward?
That's right. That's I've cut the wheel free from the bearing, and I didn't show a torque here because there's no friction on the bearing. And I've cut it feel from the ground, and there might be a vertical force and a horizontal force because this is rubber. And then I calculate sum of moments about this point and calculate that this thing has to be 0. And if you have trouble with that calculation, you're probably thinking, oh, this wheel has a little bit of inertia. But then you think, well, how much force does it take to spin up a wheel? It's small compared to the force it takes to accelerate a car. That's negligible. Yes? Other questions? Yes?
What is that force at point A represent?
This? This is the force of the ground on the bottom of the wheel. And it has, I could replace this thing by looking at, here's this little wheel, and this connected to the car. I could replace it with a normal force and a friction force. So I could put here a friction force equal to mu n and a normal force. And this would be an equivalent way of drawing this part of the free body diagram.
So how do you know that some of those two forces acts at the friction angle?
Because the rear wheel is sliding. And when things slide, you have the equation F equals mu n. Remember that screeching sound this car is making? That screeching is coming from sliding. It's actually coming from a friction instability because our assumption that the friction force is constant is wrong. There are fluctuations of friction force, which gives a vibration. But we're never finding that. We say squealing is sliding. We make the approximation force that during sliding, F equals mu n. Does that address your question?
Yep.
And then if you know mu, you know phi. Phi is just an equivalent way of expressing mu. It's the angle of the force rather than the ratio of the forces. Okay, now we want to solve for things here. What do we have as unknown? Well, there's a couple ways of counting. I'll call this net thing FA. We have FA as unknown. This force here, I'll call this N sub B, is unknown, and the acceleration of the car is unknown. Where do we have the kinematic assumption? This kinematic assumption is that the acceleration of this point G is equal to AGI, and we also have implicitly here that the angular velocity is 0. So here's we use our kinematic assumption. The wheels stay on the ground, the car is rigid. Okay, what equations do we have to work with here? We have mechanics. And the mechanics says that we have linear momentum balance equation. The linear momentum balance says that the sum of the forces external forces on the car is equal to the rate of change of linear momentum. For a car like this, we have minus mgj. We have plus nj. We have plus, I should call this n sub a, and I'll just leave that mu n sub a. We have, and this was n bj. We have plus n sub a j, and we have plus mu n sub a I. And this whole thing is the total mass of the car times the acceleration of g in the I direction. Now, linear momentum balance is in statics like force balance. I mean, linear momentum balance in dynamics is like force balance was in statics. In statics, we also had moment balance. Moment balance now, we're going to use for the first time today in a non-trivial way, corresponds to angular momentum balance. So we have our angular momentum balance equation. And our angular momentum balance equation goes like this. The sum of moments relative to any point we want. So I'm going to put a point here that I haven't picked what that point is. This is any point is equal to the rate of change of angular momentum relative to that point. So just like in statics, you could take moment balance about any point. In dynamics, you can take angular momentum balance about any point. In statics, you took the sum of moments is equal to 0. In dynamics, it's not equal to 0. It has to do with something to do with the acceleration of mass. Now, in problems with a rigid object that is not rotating, this comes out to be a simple thing. It comes out to be the position of the center of mass relative to point C crossed with the total mass of the system times the acceleration of the center of mass. And this is just what you had for angular momentum of a particle. Remember when we had F equals ma, we could take r cross both sides and get r cross ma is equal to r cross F for planetary motion and anything else. But we have another term in general, which is an I. That's the moment inertia about the center of mass, omega k. But now for these simple problems, to start with, we're going to use that the angular velocity is 0. And actually, this equation, in general, there's more stuff over here in 3 dimensions. And this particular thing is only true for a 2D rigid object. So the angular momentum balance equation in general has this term plus other stuff. For a rigid object in 2D, that other stuff is this. In this problem, that other stuff is 0. Now, what do we have on the left-hand side here is we have the positions of all of the forces relative to point C crossed with all of the forces, and we have to add that up. In this particular problem, we know a little more. We know what that acceleration of g is. We've made the assumption that the acceleration of g is a scalar in the I direction, so we know the direction of that. That's reduced to a scalar. I can't really write much more over here until I pick the point C. Or if I want to leave it abstract like this, I have to put all of these different forces over here. So I think I'll fill that all the way in. We have the position of A with respect to C crossed with, and what do we have at A? We have N A J plus mu N A I. And then we have plus the position of B with respect to C crossed with N B J. And then we have plus the position of G with respect to C crossed with minus mgj. And that whole thing then has to equal the position of G with respect to C crossed with magi. So this becomes our second equation, and this is our first equation. And how many equations and how many unknowns do we have? If we take some point C, we can't really do anything until we pick a point C. But once we pick a point C, how many equations do we have there? Think about that for a minute. I'm going to erase these first two blackboards. Any questions about these first two blackboards? So first of all, some of you are going, whoa, this all of a sudden got all kinds of arrows and hats and vectors and so on, and I warned you. So make sure you really go back and study Chapter 2 on vectors and so on. We're going to need that for the rest of the course, including today. Okay, I've got to wait for these blackboards to dry. While we're waiting for them to dry, you guys have to ask me questions about what's on the blackboard already. Yes? We can use any point we want. Just like in statics, for one free body diagram in 2D, there's three independent equations. If you take linear momentum balance, like force balance, that gives you 2. Angular momentum balance around the point of your choice gives you a third. Why is this vector equation just one equation? It's because every term is in the k direction. There's only one non-zero component in this vector equation, because it's all cross products of vectors in the plane. This is 2 equations. We could instead take angular momentum balance about 3 different points. That would give us 3 equations, and that would replace this one. No matter what you do for one free body diagram in a 2-dimensional problem, you can't get more than 3 independent equations. So which point C is it? If we take linear momentum balance, this is an independent equation no matter what point C we take, but we can pick whatever point C we like. Yes? Right here? That's the same term. This acceleration of point G. So the rate of change of angular momentum of a system is r cross ma of the center of mass of the system plus other terms about motion relative to the center of mass. In this problem, where we have a rigid object that's not rotating, there is no motion relative to the center of mass. And so all we have is that r cross ma term. Yes?
In the bottom equation, why do we have two terms that have r?
Why do I have 2 terms that have rg with respect to c? I actually have 3 of them. 1, 2, 3. Oh, yes, sorry. A, B, G, G. This has to do with the force side of the equation. You're talking about this term and this term? Yeah. Okay. We have to look at the sum of the moments, and that has to do with the forces, and there's a force at point G. And that's equal to the rate of change of angular momentum, which has to do with the acceleration of mass, and that's r cross ma, and that's also the position of G with respect to C. It's 2 different things, the left side of the equation and the right side of the equation. How are we doing on the blackboard drawing over there? Okay. So for any point C, your choice, we have 3 equations. How do we get 3? Linear momentum balance gave 2. Angular momentum balance gives 1, because it's all in the k direction. 4, and then how many unknowns do we have? We have the reaction at A. We could say mu times NA, but we know what that is because we know what mu is. We have the reaction at B, and we have the acceleration of G. So we have 3 unknowns. So we have 3 equations and 3 unknowns. If we want to find out the acceleration of the car, we just set up these equations, 3 scalar equations, pick whatever point C we want, and we can solve them. Okay, so the method is, the brute force method is write 3 equations in 3 unknowns and solve. And that's okay. That's fine. That's legit. You should be good at it. Now remember these 2 guys with the string. If I wanted to figure out how much they accelerated, I could have written F equals ma for one, F equals ma for the other, the restriction that they both have the same acceleration, taken those 3 equations, solve them, and I'd get the tension, the acceleration of one, and the acceleration of the other. But I could finesse that. I could work around it. I could find a trick to avoid that by using linear momentum balance of the whole system and saying that the whole system had a mass of 2m. Never mind that string. All the parts are moving together. The force is the total mass, 2m, times the acceleration of the system. So with those 2 guys in the string, I could finesse all the details, 3 equations and 3 unknowns, by doing the clever thing. So just like that problem was 3 equations and 3 unknowns, but we could find a trick around it. This is 3 equations and 3 unknowns, and we can find a trick around this too. It's okay to do 3 equations, 3 unknowns, but we can find, for example, the acceleration of the car without finding the reaction forces. It's not that they're not important, just like it's not that the string's not important, but you can use the properties of the string, namely that it makes the 2 things move together, to finesse that problem with the 2 masses. Here we can use the kinematic assumptions to finesse this situation. Finesse means get around, find a tricky way to get around it. Look up the word finesse in the dictionary. I was trying to avoid using the word finesse, and I wanted to use the dictionary definitions, and it came out that I was going to say, instead of finding these things, we can use delicacy and tact to figure them out. Okay, now, so the question is, can you think of a tricky thing to do to find the acceleration of the car that is without finding those reaction forces? Can we find one scalar equation and one unknown? Let me just warn you, the thing I'm about to show you is kind of a trick. But it's a kind of a trick that works lots of times. The main thing you want to know is setting up 3 equations and solving 3 equations. Brute force method. The tricky thing is if you'd rather do something tricky than do algebra and use the backslash command and stuff like that. Okay, while you think about it, any questions about the problem so far? Does anybody not think that they could do this algebra and get this answer to this problem? What would the answer be? Finding the acceleration and the 2 reaction forces. Okay, now how about the tricky thing? Anybody got any ideas? Yeah? Let me just guess that you got an A+ in TAM 2020. Okay, well, you should have. That was really good. Okay. So let's look at this free body diagram. We have an unknown force here. but we know its direction. And we have a force here, and we know its direction. It's in the direction of phi, where tan phi is equal to mu. And since we know its direction, we can do this geometry problem, and we can find this point here, and we can use that point in C. Now, if we take angular momentum balance about that point, we're going to take the sum of moments of all of the forces, and that's going to be the rate of change of angular momentum. There's this force, mg, but we know that one. So it's OK leaving it because we know it. We know the mass. We know the gravity. This one we don't know. It has no moment about C. This one we don't know. It has no moment about C. Therefore, we have one equation and one unknown if we take sum of moments about C. Now, information about these forces comes into the problem. How does it come into the problem? Well, here we have the angle phi, and here we have a height all the way from here to here. What is that height? Well, L, remember the length of the car, over this height is equal to tan phi. So this height here, I can call it h, is equal to, how did it go? We had L over h was equal to tangent of phi. Therefore, h is equal to L over the tangent of phi, or L over mu. So h equals L over mu equals L over tan phi. Therefore, we can write sum of moments relative to point C equals h dot relative to point C. We could have used any point C we want, but if we use this particular point C, then we have to do the math right. What are the moments with respect to C of all of the forces? We've got to get the positions of the force crossed with the force. What is the position of point G? So we have the position of point G with respect to C crossed with minus mgj. And then we also have that this is equal to the position of G with respect to C crossed with MAI, A of G. So now we have a little geometry problem to work out, which is we have to fill in what is the position of G with respect to C, and it's minus little c I minus h minus h j. And that we can put in both of these places. H, we know what that is, so this gives us one equation and one unknown. I think class ends this minute. Is that correct? So there's enough here now that this is reduced to algebra, one equation and one unknown. Okay. I think that for most of you this is a relatively difficult class, but it's one that you want to master. You will have learned something in the process. In your homework, you not only have a problem like this, you have a three-dimensional problem with very much the same spirit. So we're challenging you here this week on the homework.